Kevin O'Brien on BH sets, please.
All right. All right, so we've got this little X up in the corner. It's just going to be covering the word the in the title of every slide. So let me just start by making sure we're all on the same page. H is always going to be a positive integer, and a B sub H set, this is a standard object in combinatorial number theory. Set A is a B sub H set unless there is a non-trivial solution to this equation where we've got, let's see if I can mark on this thing, the sum of H elements equaling the sum of H elements in the set. That only happens if they're the same things. Maybe rearranged, but they're the same collection of numbers from the set A with the same multiplicity. All right, so another way of expressing that, move that to rearrange my windows a little bit. There we go. All right, so another way of saying this, if you give names to the to the elements of your set, then you can sort the summands according to your names, and you can just record the multiplicities. So here the m's and the n's are multiplicities for each a sub I in the set. And we say that it's a B sub H set unless there are non-trivial solutions to that equation. Right? So H of them adding up to the same thing as H others of them. And trivial just means that the multiplicities would be the same. So those are our B sub H sets. Sort of a trivial case, let's go ahead and get it out of the way. If H equals 1, it's a positive integer, why not? Then the definition results to it's a B sub 1 set. I mean, it simplifies to if it's a B sub 1 set, unless there's a non-trivial solution to, well, just one summand equaling one summand. So of course there's no non-trivial solutions to that. So we get everything. The natural numbers is a B sub 1 set. Okay, so H equals 1 is handled. From now on, H is at least 2, except for one moment later in the talk. And so there are some obvious counting bounds that are folklore. They get used occasionally in the literature, but there's no real citation for them. One is that if you've got a B sub H set with k elements, then you've got k plus H, choose k different sums that you can write. And if those are all going to be different, then you have to have spread of things, right? So the smallest sum is going to be 0 plus 0 plus 0 plus 0. And then the biggest one is going to be AK plus H times AK. So just that number of sums has to fit in an interval of that length. And you rearrange what that means. And it says that A sub k can't be too small, or these sums just, they don't have enough space to spread out. You can, there's a trivial bound in the other direction. A sub k can be any number except one that is like this. And if you imagine A sub k equaling that, then you can rearrange that to where you've got H of the sums on one side and H other sums on the other side. So we would get a solution to this thing that you can't have a solution to if it's a B sub H set. So we're not allowed to have A sub k having this form, R being the multiplicity of A sub k in the violation. We call these, I call these forbidden numbers. And there aren't infinitely many forbidden numbers. So you don't have to take A sub k to be huge. You can take A sub k small enough to avoid all of these forbidden numbers. And you can do that while having A sub k being not too large. So of course you can make a B sub H set by just having the set grow so rapidly that, that you don't get any overlaps of these sums, that the sum is determined by the biggest element, the biggest summand. But the question is, how compact can we make it? And this gives a bound to how compact we're definitely allowed to make it. Okay, so I'm going to be talking later about a greedy B sub H set, and this is going to be literally a bound for the kth element of the greedy set. Okay, so we've got these combinatorial upper and lower bounds. Okay, so let's focus in on the most common case. So the most common case is H equals 2. So we're talking about a sum of two elements equaling another sum of two elements is forbidden. Unless they're trivial, and here trivial just means that we've got the same thing rearranged. Of course, 3 plus 5 equals 5 plus 3. That's a trivial solution. What's actually forbidden are things like 3 plus 5 equaling 4 plus 4, where you've got different numbers on the two sides. You can rearrange that, and this is an interesting and oft-used observation. You can rearrange that to be about differences instead of about sums. Because H equals 2 is special, you can move the y2 to the left and the x2 to the right, and you get a difference. And what trivial means is just that we're talking about differences that are non-zero. So a B2 set, yeah, the sums are all distinct except for the trivial rearrangements, but it's also true that the differences are distinct except for the trivial zero differences. Okay. Both of these definitions, I mean, I could use either of these as a definition for B2, and when you pick up a journal article, it's probably about 70% use the difference definition and 30% use the sum definition. Either way, it's pretty obvious that these B2 sets are preserved by shifts. If you add 5 to everything in the set, then you add 10 to all the sums, so distinct is still distinct. And you leave the differences unchanged. And it's also holding for dilations. Yes, Kevin, repetition is allowed in the sums, explicitly allowed. There is a variation for B2 sets. Sometimes people want the sums to be different, and we call those weak B2 sets. It's unclear exactly what weak should mean when we're talking about B3 sets or B4 sets. Do you want them to not be all the same, or do you want them to be all distinct, or what exactly do you mean by that? There's gradations of weakness that come up. Okay, so these sets have been around for a long time. The earliest occurrence that I'm aware of is in a harmonic analysis paper of Sidon. This is from 1932. And you can see here in a statement, we have Zahlen, that's the Z that we use for integers. So he's got these positive integers, and he's looking at I've lost the ability to scribble here. A second ago I was scribbling. There we go. So he's looking at the doubles of them, and then he looks at pairwise sums. Pairwise sums when they're distinct, and differences that are distinct in this. And he insists on the property that in the sequence of numbers that includes all the doubles, the sums, and the differences, everything occurs at most k times. So that's a little bit stronger than just wanting the pairwise sums to only appear one time each. Or I should say that's stronger and weaker, right? He's wanting the differences to also be involved. And he's not insisting that they all be unique, just that there's a bounded number of repetitions. And if he has such a sequence, then he can use that as the support for a trigonometric polynomial that has some particular properties that were interesting for him. And he's got this footnote where he says that he can find such a sequence that grows like n to the fourth. So this is how Sidon was a friend of Erdős, and this is how the problem comes into number theory historically. Sidon tells Erdős about it, and then Erdős generalizes it and specializes it and publishes some papers in the 1940s. So a separate recreation of this happened. This was in the Scientific American magazine. Martin Gardner had a column for decades in that, and he wrote. So I find this almost incomprehensible, but I know what he's trying to say, so I can make sense of it. So, so as Golem points out, instead of just reading it, let me paraphrase what he's saying. Right. So he's wanting to represent the complete graph on n vertices, where you align the vertices on a straight line at integer points, and the edges you represent by how far, you can label by how far apart the vertices are. And if you choose your vertex points correctly, then all the edge labels will be distinct, and you have a nice compact presentation of a graph, right? Every subgraph of the complete graph is a subgraph here that you can get by just listing the edges, and the edges are just numbers. Okay, so this would be in some ways, a computationally efficient model for a graph. He was unaware, Golem and Gardner, unaware that this had been looked at by harmonic analysts in the 30s and number theorists in the 40s and 50s and 60s. And so these came to be known as Golem rulers, and there's a large literature of people thinking about Golem rulers that aren't aware of that other literature that preceded them. And still, when people do computational work, they tend to call them Golem rulers. I wrote a thing that I called a complete bibliography, although I knew it wasn't complete, as part of my thesis 25 years ago. A complete bibliography of B sub H sequences, Sidon sets, maybe I call it. And at the time, I didn't know that Golem rulers existed as part of the literature. So that's this whole literature, this whole computational stuff is not included in my complete bibliography at all. Carl Levy and I are working on an updated version of that bibliography that will have this in it. Another earlier occurrence, this is from the 1950s, shows up in electronic engineering. So the problem was to assign radio frequencies in a way where they wouldn't interfere with each other. And Babcock is worried about these intermodulation, third order intermodulation interference that occurs when you have three frequencies that satisfy an equation like this. Of course, if you rearrange that, that's A plus B equals C plus D, which is a thing that he wants to avoid this interference. So he's exactly asking for a B2 set. And he hand computes B2 sets for up to 10 elements. He misses some that are better. And up until the 70s, judging from the IEEE literature, his 10-element B2 sets are being hard-coded into satellites, even though they're not close to optimal. So people actually care about these things in a practical sense. And to avoid fifth order interference, he's talking about equations like this, which is A plus B plus C equals D plus E plus F. That's a B3 set. So he's worried about, third order interference, avoiding that gives him requires him to take a B2 sequence. Avoiding fifth order interference requires him to take a B3 set. You might ask, what about fourth order interference? Why is he skipping over that? And the fourth order equations of this sort aren't translation invariant. And if you think about the frequencies, like FM radio stations, they're between what, like 85 and 104, 105. So if you've got a sum and difference of 4 of those, it can't equal to a fifth one just because they're all going to be around 100, right? The parity ends up off. You're going to be around 0 or you're going to be around 200. You can't get back to around 100 like that. So that kind of interference is somebody else's problem, whoever's using that part of the spectrum. Okay, so I've tracked down about 50 articles where they're working on this and variants of it in IEEE journals. Carl and I have, and it will be in the new version of our bibliography when that comes out, which could be any day now, but probably not for a couple of months. Okay. Okay, so our basic problem here, right? So we've got this definition of a B sub H set. And my indexing here is a little off. Let's start with A0 and go to A1 up to AK. So for a given H and K, find a B sub H set that has K elements and has the diameter being as small as possible. So it's translation invariant. You can assume that the smallest one is 0, and then you're really just talking about making AK as small as possible. The phrasing that has usually come up in number theory, in the number theory literature, is you fix the diameter, the diameter of the set's at most n, and you're trying to make the set as large as possible. So they're equivalent questions, just phrased a little bit differently. And one can ask for infinite B sub H sets, and there is a sparse literature on that. That problem seems, to me, it seems a lot harder. And I have never found anything interesting and new to say about infinite B sub H sets. Though I've made a career talking about the finite ones. Okay, so let's look at a construction of this. Still in the survey territory, right? This is 1938. Singer looking at, I think he was trying to do computations in projective geometry, and he wanted to have a good labeling of points and lines where he could quickly discern if a point was on a particular line or not. The theorem, as it concerns us, is if you take a prime power q, then there is a B sub H set modulo something with q plus 1 elements. So for example, there is a B3 set modulo 1464 with 12 elements. Okay, so what I mean by a B sub H set modulo something is that not only are the sums distinct, but they are distinct modulo 1464. So that modular thing could introduce some extra collisions, but it doesn't. For these particular sets, it doesn't. Usually it would. Okay, so
There's something I'm not quite getting here. Let Q be a prime power. There's a BH set who's H over here. I mean, in this statement.
Of the example or the theorem?
The theorem.
Yeah, so there is a B sub H set.
With H equal what?
With any H that you want. Any positive integer, at least 2. I don't know, maybe works with H equals 1
I see,
also.
okay, yes, it's showing up in the power of, okay, yeah, okay.
Yeah, so the H reappears in this modulus. But not in the size of the set.
So H and Q here are independent. So you can say, let Q be a prime power and H any integer, then there's a BH set. You can put H into the statement of the conditions. Yeah.
Yes.
Okay.
Yeah. Okay. Okay, so another way of saying this around, right? So this gives us B sub H sets with a prime power plus 1 elements. But not every number has that form, luckily. Number theory is interesting. So if you just pick a K and I ask for a B sub H set with K elements, well, we can still kind of jerry-rig that into things a little bit. By taking Q to be the smallest prime power that's at least K minus 1, and then we get a B sub H set that has Q elements, and you just forget about some of them to make it down to have size K. And so if you look at the subset of a B sub H set, that's also a B sub H set. So you can get down to K. But this highlights the weakness of this result, that we need to find a prime power that's at least K minus 1. And that is the error term that comes when we start talking about how big these are. The error term is driven by that need to find a prime power. And finding prime powers is a challenging problem. Okay. Well, okay. Giving formulas that guarantee prime powers is a hard problem. So another way that we can say it is, okay, for every prime power Q, there's a B sub H set where we go A0 up through AQ, right? That's Q plus 1 elements. And the AQ is at most, well, the modulus. Okay. Relevant to this, that I was saying that we have this difficulty about finding prime powers. We know that, thanks to Baker, Harmon, and Pence, that there is a prime between x and x plus x to the 21 over 40. Usually here means if x is large enough. For all sufficiently large x, there's a prime between x and x plus x to the 0.525, which is a little bit more than x to the 1/2. So that guarantees that we don't have to go too far above k before we find one of these sets. But as I say, this is the error term, then the bound that comes out. Okay, so we get out of Singer sets something a little bit more than just a B sub H set. It's a B sub H set modulo something. And if you just forget the modulo part, then it's a B sub H set in the integers. But before you forget the modulo part, you can take advantage of it. Because shifts in the modulo sense are still going to preserve this B sub H property, and dilations modulo M are going to preserve this B sub H property. So you get this affine collection of equivalent sets that all have the B sub H property, and you get to choose one that's nice for you, right? From among all those different affine maps of the set that Singer has handed you.
Is it possible to move that arrow?
I'm sorry, what's that?
There's a kind of a very intrusive arrow on the top right.
Yes. So there's this this X up here, you mean?
No, just above the word sums.
Oh.
Ah, thank you.
Aha, I didn't know you could see that.
Right.
Okay. Is there anything else blocking your screen?
No.
Okay. So there are some things blocking my screen, but you don't see those, but you saw the arrow. Okay, so I'm learning here. Yeah, so the X up in the corner, if I get rid of that, then I lose the full page bit. So I apologize for that, but I didn't have time to remake my slides when I realized that would be an issue. Okay, so we have all these affine shifts of the thing. How do we take advantage of that? You can find a dilation and a translation that makes a large gap and shift it so that that large gap is at the very end. So when you lose the modular part, your set has a smaller diameter than the modulus, and maybe even much smaller. All right, so I'm going to come back to that in a little bit. I want to speed up a little bit maybe. So let's step through how Singer's construction works, because I want to present a generalization of it that is new. So we start by taking a generator theta of the finite field over FQ with dimension H plus 1. Okay, so generator of the multiplicative group. So all of these different powers of theta are different. And then we just set M to be this thing, which is going to turn out to be our modulus. And here I've blessed you with a picture for Q equals 13, H equals 3, right? So this is some, this is 13 to the 4th minus 1 elements, right? Minus 1 because 0 isn't in the multiplicative group. So that's some 28,000 plus elements. This black circle, that's actually a bunch of dots, but 28,000 of them, so it looks like it's continuous. If you look at the powers of M, of course, this f13 to the fourth has f sub 13 as a the multiplicative groups as a subgroup. And that multiplicative group has 12 elements. So we see these red numbers here like numbers on a clock going around. That is the multiplicative subgroup of FQ that lies inside this FQ to the fourth. There we go. Okay, so those, the interesting bit there is that powers of theta to the m are in the base field. Okay, so we set S. This is the magic set Singer will have, but we'll massage it a little bit before we get there. We let S be the exponents, where theta to the a equals u times theta plus v, where u and v are in the base field. Now I've made this theta here, I put a hat on it, and I made it a different color. Don't worry about that just now, it's the same theta. But we're going to use different properties of this magenta theta than we do of the non-magenta theta. So S, we get one thing in S for each u and v, except for u and v both being 0. Because when they're both 0, it's the 0 element, which isn't representable as a power of theta. So the other q squared minus 1 such elements each generate an exponent. But if we take a, hold on a second, maybe I can, all right, I'm writing real thick. If I look at theta a plus km, that's theta to the a times theta to the km, which is theta to the a times something in the base field. And theta to the a, here is my u theta hat plus v times c. And that's a uc theta to the hat plus vc. And uc and vc are in my base field. So I'm just getting another element that was already in S. So everything that is in S, if I add a multiple of m to it, I get another thing that's also in S. Unless I fall off the end of it because, because this is modular, but I'm only taking up to q to the h plus 1 minus 2. So this set S has a natural mod m structure. And when we reduce like that, we find that S has q squared minus 1 over q minus 1 elements modulo m. Q squared minus 1 over q minus 1 is better known as q plus 1.
Yeah.
That's the size of our Singer set. And I've put this S here in these green dots around the inside. And you can see that, okay, it looks the same here as it does here, as it does here. That's that it's mod M, really, with this set. Okay, so what does all that have to do with the Sidon property? If you had a violation, if you had some sum of the x's equaling some sum of the y's, mod M, then I could raise theta to both of those. And theta to the km gives us something in the base field. And theta to a sum is a product of thetas. And each of these thetas in our S, I can rewrite as a linear term in terms of theta. And now, for a moment, I'm just going to use this to define a polynomial. So I'm going to replace this theta with some variable, z. And I get some polynomial in z, and I get a different polynomial in z. I've left out the term c here on purpose in my g. But, so I've got these two polynomials, and f of z minus constant times g of z. This is a degree h polynomial. The coefficients are in this field FQ, and it has theta, actually theta to hat, as a 0, but theta generates the multiplicative group. So it has to, of FQ to the h plus 1. So it has degree h plus 1, if you have a degree h+1 thing that's a root of a degree h polynomial, the polynomial has to be identically 0. And so this forces f to be equal to a constant times g. And that means that by unique factorization over finite fields, that the roots of f and the roots of g are the same. And I hope you forgive my abuse of notation in the next line. It's possible that one of the u's is actually a 0, and so it doesn't have an inverse, and we have to have a little bit of special care around that, which I'm ignoring because I'm on slides. But once you get that the roots are the same, it's just a little bit of rearranging symbols to get that the sets that are giving rise to these are the same. Okay, so note here before I move on that about theta, we used that it generates the multiplicative group of fq to the h+1. The theta hat, the only thing I used about it is that it has algebraic degree h+1. There's no reason those have to be the same. The same theta works in both places, but it doesn't have to be the same in both places. Okay. All right, so I'll return to that observation in a moment. So here's a practical guide to how you go about getting a thick B sub H set. You want to have k elements. Okay, so you start looking through k-1, k+1, k+2, so on until you find a prime power. That's your Q. You use Singer's construction to get you a set that has q+1 elements. And then you just toss out some elements to get it down to having size k. All right, so that's pretty straightforward.
If you're a concentrator,
we
you
would-
wear it like a purse.
We'd like to be able to get thicker
That
ones.
makes sense.
Okay, so is there a better way? So Bose and Chawla, this is not sure of the date on this, maybe 1960 or so. Don't quote me on that. Have a way to get B sub H sets that is less computationally intensive, and they tend to not be quite as thick as Singer sets. And for the case when H equals 2, which is the primary case people have been interested in, Ruja has one that it turns out appeared earlier in some article of Spencer that I haven't seen, that is much faster and still just a little bit worse than Bose and Chawla. Right? So there's some trade-off here between computation and quality. But there's also quite a few tricks that we can use, and I've already talked about that a little bit. This we can dilate and translate to try and do better, to try and get so that when we throw out elements to get it down to size k, maybe something better happens, these tricks. All right, so here are some of the tricks that people have used. One is that you don't just have a gap at the end, you can move to have the largest gap. Right, so you've got q+1 elements mod in, that's q+1 gaps. You can move so that the biggest gap is at the end. And the biggest gap is at least as big as the average gap, so you get something. Here, the term that we're subtracting off has order q to the h-1, which is the same as the error terms, right? So that's a meaningful improvement. More than that, the gaps have to be distinct from the B sub H property, so that makes it even better, right? That the largest gap can't be the average gap, it has to be bigger. They have to spread out some. An idea that people have looked at, I think everyone who's worked on this problem has tried, is you dilate to make the largest gap bigger. And it seems computationally like there's a logarithmic factor that you could do here, but nobody has proven that there's a logarithmic factor that's available by dilating, by choosing a good dilation. There's kind of a dual idea that accomplishes the same thing. You can dilate around to make some constellation of elements in the set to be really close together. And that means that the average of the other gaps has to go up. And so, and another idea that bears fruit is maybe the first prime power isn't the best one. Maybe you keep going and get another prime power that's even bigger, and you have to throw out even more elements, but you end up with something that's thicker. Computationally, these are all meaningful, important ideas, but there's no theorem that says that how these things work in general. People have tried, including me, and it's a hard nut to say what dilating these sets actually looks like. Okay, so I alluded to this earlier. We need a theta that generates the multiplicative group and this theta hat to have algebraic degree h+1. These don't have to be the same thing. We can let theta hat be some other element of degree h+1. We can write down such an element as some other power of theta. So instead of theta hat here, we can write theta to the b. Another idea is that what if we had a different generator of the multiplicative group? You had a tau instead of a theta. Does that help at all? Does that give you more sets? But the tau would be some power of theta, right? So the tau would be theta to the t, say. And then the tau to the a would really be theta to the ta, and we're just multiplying the a's that we get by t inverse mod m. And so we just end up with a dilation of our set. So choosing other generators doesn't get you more than just dilating things does. But that frees us up a little bit, that we don't have to worry about the generator, so we can fix a particular representation of the finite field. Conway has done that. It gives a not quite canonical representation, but it's uniquely defined at least, and it has some good computational properties. So if we use that, then we can define this. And one is then led to ask, does this B actually help? Maybe changing the B is also just some affine change in the sets S. And the answer to that question of does B help is that sometimes. So here is a theorem from the fall. This is published in Journal of Integer Sequences with some other stuff. That if HQB is in this domain of the Singer set thing, right? So H is a positive integer, Q is a prime power, and theta to the B, where the theta comes from the Conway representation of the finite field, FQ to the H+1 has degree H+1. And HQE also, right? So these are giving Singer sets. They give affinely equivalent Singer sets if, well, okay, so you can read what's going on here, right? If B is congruent to E modulo this, or if B is congruent to P times E modulo, oh, it's a different modulus. Or if theta to the B minus theta to the E is in the base field, and so on. So these conditions combine, right? So if you imagine a graph where the vertices are all the possible values of B, and you connect them if they're giving affinely equivalent Singer sets. Right? So condition 1 gives you a bunch of edges, and condition 2 gives you some new edges, but then you have to go back to condition 1 because the new edges you got in condition 2 tell you new things in condition 1. And then condition 3 gives you some new edges, but then you have to go back to condition 2 and then back to condition 1 to get yet more edges, and then to condition 2 to get more edges. And finally, this condition 4 is kind of an annoying beast that I wrestled with some, but I couldn't simplify, unfortunately. So as a corollary, when H equals 2, this every B and E are equivalent. So for H equals 2, the Sidon sets, Golomb rulers, this idea of separating the theta and the theta hat doesn't actually help at all. But for H at least 3, it usually does. You get a lot of different affinely inequivalent B sub H sets with the same modulus, and some of them you can dilate better than others. As far as I know, these conditions that I wrote, and I have in the paper, I also have conditions for the Bose-Chawla construction. As far as I know, they are necessary and sufficient. But like I said, they're not, you have to iterate them, right? So sometimes a B and E are equivalent because of some combination of these conditions. And this fourth condition here, like annoyingly, I'm not aware of anywhere where you need R to be other than 1 and T to be other than 0. So I suspect that simplifies, but I don't know how. Okay, so there have been a lot of computations around B2 sets. So distributed.net, they do these distributed computations. They spent 8 years on tens of thousands of machines computing the optimal Golem ruler. That's a B2 set with 28 elements. That's the biggest computation I'm aware of. And it's for B2 sets. And Dogon and Rokicki have done this massive computation, and it appears in this journal on recreational stuff, right? It's sandwiched between an article on origami and an article on designing good crossword puzzles, and it's completely not covered by MathSciNet, but it's got some really good math in it. It's not just a matter of letting their computer run. They've done some clever things that they explain. Here's an example that number theorists are unaware of. It's often said that Erdős asked that maybe K is less than or equal to root n plus big O of 1. If true, that big O of 1 term has to be up at least around 41, just by these examples. Right, so that's looking like maybe it's not true. It's often said that he conjectured that the size of the set is at most root n plus big O of n to the epsilon. But this data set of Dogon and Rokicki suggests no, that the actual error term is n to the 1/4. Of course, you can't tell from computations if it's n to the 1/4 or n to the 1/4 over log n, or even n to the 1/4 over log n, right? We don't know what the coefficient exactly is, maybe a half. And another example that's come up sometimes as a question is whether or not there's always a B2 sequence that's greater, whose cardinality is greater than the square root of its diameter. And they exhaustively give examples all the way up to 500,000, except for 3 set sizes. So it might be that there's a counterexample to this conjecture, if anybody has conjectured it, with 492,116 elements. Okay, so I am running out of time. I've budgeted like I'm going to need 2 hours to get through everything. So for B2 sets, I just want to mention this. There's been incremental improvement in the bound. The end of the 1/2 term is correct. It's asymptotically correct. We don't know what the error term is. And just a couple of years ago, that error term got improved by triaging 2 different inequalities. And then that has improved recently. My result here, I wouldn't say it's an improvement. You notice I have to give more digits to say that it's an improvement, right? If I only give 3 digits, then I have to say 0.998, which was the same. So I gave more digits so I could show that there's an improvement, which indicates how slight it is. But the advantage is that it's simplified, that I'm not triaging 2 inequalities from 2 different proofs. I'm triaging 2 inequalities from the same proof. And then Zach Hunter, oh, you can't see it here. Okay. Zach Hunter, this is currently being refereed, and Daniel Carter and myself. Zach is the one who had this idea that you can triage one of the inequalities against itself with different parameter inputs. And we got it down to 0.98 something. So it's a more marked improvement in the number, but that's improving month by month. So there's finally some movement in that problem after 70, 80 years. Okay. There's been no real computational work for B3 sets, right? The computational work was driven by this Martin Gardner column, and he's just talking about B2 sets, Golem rulers. And the people who are doing the computations are myopically focused on that, right? They're not aware of the number theory stuff in general. As far as I know, ideas of Ben Green from his thesis give the best bounds for large H, but they're inexplicit and kind of clumsy to work with. Carl and I Carl's here somewhere, I see his name, are working on updating the bibliography, and in that we'll have a list of the best bounds for the best bounds for each H. It's a thing we need to have in there. Okay, so another idea is instead of bringing the diameter down, bring the size up. The way you would do that is you get some B sub H set, and then you put in some extra elements. You just sort of greedily look for, hey, maybe I can add in a new element without getting too big. And Bose has a paper in the 40s where he mentions a way to do this in general as just kind of a throwaway comment, buried on page 3 of his paper about something else. And it hasn't been picked up on by the computational people or the theory people. But if you have one of these modular Sidon sets, or modular B sub H sets, you can always add in an element with a particular structure. That's your next greedy element that you would put in. And it's not too much bigger than the modulus, right? If H equals 2, it's just the modulus plus the, sorry, that should be an A1, plus the second smallest element of the set, right? So it's really just a small growth in the diameter and a small growth in the size. But it raises the question, how does the greedy algorithm behave with this Sidon property, right? So you've got some B sub H set, and you start greedily adding on elements to it. How efficient is that going to be? Okay, so yeah, so here's a mention from 1944. This is the earliest case I'm aware of the B sub H notation appearing in the literature. They call these the B2 sequences of Sidon. And they're just defining the greedy one where they start with 1 and 2. I'm going to shift those down by 1, start with 0 and 1. And let's see what we can say about that. And so,
What journal is that paper?
The
Mia Chawla paper?
I don't know. It's a 2-page paper.
Sorry,
and if you look in my bibliography, my complete bibliography, which was in the Electronic Journal of Combinatorics,
right,
it's in there.
Yes. Okay, thanks.
Mm-hmm. But it's a 2-page paper. They define this greedy algorithm. They ask some questions, and there's no actual theorem. Like one of the things that they observe is that the kth element is at most k plus 1 squared in this notation where I've got gamma 0 being 0 and gamma 1 being 1. But that fails at 360, right? So they didn't have more than a dozen or so elements of the greedy sequence even. Of course, today we've got more terms. The Online Encyclopedia of Integer Sequences has 25,000 terms. And it looks like it's growing like k to some power that's trapped between 2 and 3, but it's increasing. So it starts out a little bit below 2, and it climbs and it climbs, and it gets past 2.5, and it keeps going up. It gets up at least to 2.527.
Just a side comment. When this paper was written, India was still under British rule.
Was still what?
When this paper was written, India was still under British rule.
Yeah. Right. So this is a whole other world.
Yes.
That they're working on. Another thing that this is a very rare paper where the authors are out of alphabetical order.
Yeah.
So I'm guessing, since Chawla is the much better known person here,
yes,
that Chawla was an advisor, and Mian had done some work, and Chawla was helping Mian out by letting him list first on the author list.
Chawla's daughter was a student at Harvard, and she and I took the same course with Oscar Zariski.
Uh-huh.
I don't know what happened to her, but she was in my class.
Excellent. Excellent. Yeah, so this looks to me like a moment of Chawla being generous with credit, which is to be applauded. Right.
Yeah.
So not only do Mian and Chawla not have theorems in this paper from back of British rule, the time of British rule, nobody has in the subsequent years either. There are no theorems about this set. We don't know what the actual growth is. At the very beginning, I gave those easy combinatorial arguments for bounds for it. That is the only theorem sort of thing, right? Is 33 ever a difference? It's not a difference among the first 25,000 terms, but maybe it comes up later. Not sure. 1 through 32 does appear somewhere in there. If you look at these, one way to measure the size of a set is looking at the sum of reciprocals, and it's known to not maximize that, but the proof here, it's not really it's not an explanatory proof. It's just, hey, look, here's a better example that gets the sum of those reciprocals is even smaller. Okay, so if we're looking at this, right, the first row is the natural numbers, right? So this is a table that's now in the Encyclopedia of Integer Sequences after some work that Mel and I did in the fall. So the first row is the greedy B1 set, the natural numbers. The second row is the greedy B2 set, that's the Mian-Chawla sequence, about which nobody has ever managed to say anything theorem-wise, right? It's all computational work only. And then we have the greedy B3 set and the greedy B4 set. So these rows are enigmatic, right? It's hard to say, so far as we know, it's impossible to say anything about the rows other than computation. But if you look at it like a table, which I was doing over the summer, then you see down the columns that there are some patterns, right? Like the second column has a pattern that's screaming out at you. And the third column, maybe it doesn't scream out at you, but if you look at the first differences, you realize that it's a quadratic sequence, h squared plus h plus 1. And I suggested this problem, and Mel and I started working on it over the fall to identify the patterns that are in these columns, right? So the first three are polynomial. What about the fourth one? Is the fourth one a polynomial? No, it's not quite a polynomial. You get some floor functions involved. And we have a proof of this. It's almost polynomial, right? You could call that quasi-polynomial, right? It depends on the whether h is even or odd. It's a polynomial on the evens and it's a polynomial on the odds. The proof is it's not easy. And even once you have the proof, like working it out again and getting everything without dropping anything is a challenge, as we Mel and I discovered through October as we wrote it and rewrote it and came up with a slightly different answer each time. But at the end of the day, it's also not really enlightening, right? This is just where a gap happens in the set of forbidden numbers. So is there a quasi-polynomial for each one? Maybe if you just do pattern matching on the computations of the fifth element, you can get a formula that appears to work out to h equals 47. This pattern holds. So I'm fairly confident that this is the fifth element, but I'm not hopeful of being able to work that out by hand. And every time I tried to computerize how we did gamma 4, it turns out that you need some cleverness in there somewhere. You need to look at it a little bit more enlighteningly. And then, Mel asked this problem, okay, so look at this table. As we go down the columns, of course, that's increasing, right? But can we prove that it's increasing as you go down the columns, except for zeros and ones, of course? And even that we can't explain. We can't, it has to increase and increase rapidly just by common sense. But by mathematical sense, I don't know. So a lot
Just
of
checking
problems.
what the issue might be. I mean, it's clear that each time you raise the H, you're adding restrictions. But it could be that because you've added restrictions, at some point you've gotten a value which will make things easier later on.
Yes.
That's
So,
what's going on here. That's why it's not clear that they're really increasing.
right, right.
Okay.
So this computation of gamma 4, right? You write down the numbers that are forbidden from entering into the set, and you need to find the first thing that isn't forbidden. And that ends up being some subtle congruential collisions. Some things are dictated by polynomial inequalities that, because 4 is a small number, they end up being, they simplify to linear inequalities, but I don't know that they would simplify for gamma 5 or for gamma 6. And I'm really skeptical that they would for higher Ks. Yeah, so you get these local things that maybe just by some coincidence, it's really, you get a lot of things that are forbidden for gamma 5 of 10 that aren't forbidden for gamma 511. Okay, so as Moshe said, right, there's this congruential property. Okay, so here are our formulas if we just look at the main term, and you see them increasing, the power of H increasing as you come up, and the coefficients. Well, okay, so you get some stuff at the beginning, and then it's 1, 1/2, 1/3. So I put a question mark here. I believe that's correct, but we don't have a proof of it for the formula for gamma 5. So you can always just multiply by H and add 1, and you could preserve this B sub H property. So once we have gamma 4 being 1/2 H cubed, we can have them all being 1/2 H to the appropriate power. Right? So we get this upper bound on them. I have improved that 1/2. Okay, so before I come to that, right, so the basic combinatorial argument gives us a lower bound that has the same order, same power of H, but the coefficient is 1/k factorial. So on the right, I'm getting 1/2, and on the left, we're getting 1/k factorial. For gamma 5, I can improve the lower bound from 1/120 to 1/8. And I'm out of, so that doesn't generalize. I don't have any non-trivial lower bound for anything past gamma 5. But for upper bounds, I do. And for gamma 5, I can pull it down from 1/2 to 0.467. Of course, I think it's 1/3. But the theorem right now for gamma 5 is that coefficient is between 1/8 and 0.467214. Surely it's 1/3, but there we go. So I'm out of time. Yeah, sorry, Andre. A hard stop should be a hard stop. So I'm just gonna.
You can keep going. It's, I mean, it's just the internet.
You make a fair point. It is just the internet. Yeah, so what's left is I wanted to give some indication of how I'm getting this this upper bound. And it's really going to be a vague indication. The interesting thing I think here is this lower bound that I can't say anything about, because I need to have the exact values, like how I'm doing it, I need to have the exact values for all the previous gammas. So I know gamma 1, gamma 0 through gamma 4, and I can use that to get a bound for gamma 5. But since I don't know gamma 5, I can't say anything about gamma 6, except back to this trivial, the easy combinatorial argument. Shouldn't call it trivial, easy though. Okay, so here's the idea, right? So we have our forbidden numbers, and if we write them as multiplicities, the forbidden numbers look like this. So gamma k plus 1 can't be anything that's like that, where the multiplicities add up to h. The other multiplicities add up to h minus r, because r is the multiplicity of the new element and why it's getting forbidden. And r can be anything from 1 to h. So you can think about this, right? We're adding together h things from our set, and then we're subtracting off h minus r things from the set. This is, if you think about that as random variables where we're picking something uniformly from the gammas that we already have. Thank you, Rohit. I appreciate you being here, and I appreciate the
It's a
comments
pleasure.
about,
Thank you. Bye-bye.
modeling. Absolutely. So this is a central limit theorem kind of thing leaping in, right? We've got a sum of a lot of independent, identically distributed random variables, and then a difference coming in, but that's easy enough to work with. But I haven't been able to use any of the off-the-shelf central limit theorem or large deviation results to make this work, but that's definitely the inspiration for what's going on, right? So the central limit theorem tells me how many of these forbidden numbers I'm expecting in an interval, and I just need to find an interval where I'm expecting fewer than there are spaces in that interval. And that means there is some number in that interval that is not forbidden. And that bounds my value for gamma k plus 1. So the goal is to look for an interval j that has fewer than the cardinality of j forbidden numbers, and then I get a bound on gamma sub k plus 1. That's it. So that's motivated by the central limit theorem, but in the end, because the sequence of gammas is increasing so rapidly, the central limit theorem ends up being really like clumsy at bounding things. Right, the variance of these xi's and yi's is almost entirely determined by gamma k, but since I don't have lower bounds on the others, I can't make that into a theorem. That my variance has to be huge because of that. Okay. Yeah, so that's what I want to say about that. And then I guess I've already highlighted these greedy questions, so I'm going to skip repeating that. And that is maybe my last slide. That's the last slide. So thank you all, especially thank you for letting me run 5 minutes late. I hope that's not too much of abuse of you.
Thank you very much.
And I'm done.
Thank you.
Thank you. Thank you.
Let's see, questions for Kevin. So actually, Kevin and Carl, is your revised, updated, expanded bibliography on sit-on type sets finished, or are you still working on it?
Oh, we are still working on
We're
it.
still working on it.
So
I have the overleaf open right now, actually.
No, because I thought you said it was about to appear. So I just looked at archive and I didn't see it there. So, okay, I understand.
yeah, so any day now, in the next couple of months. So we had my old version from 20 years ago that was had almost 200 articles about sit-on sets. And now we have I don't know, Carl, what's the most recent number for how many papers are in there?
I mean, I don't even know. I'm just going through and sorting them. So I don't even, was it 300, 400? What did we
So
jump in
there
there?
was 450 at
Yeah,
some
yeah.
point a couple of months ago.
Yeah.
And we're
Something
still
like
finding more as we, every time you actually take a look at one of these articles, they reference something, and often it's something we also didn't know about. Yeah, so it's probably going to end up being around 500 papers, this version. And it's you can't really do a search for B sub 2, right? Because there's this math formula stuff isn't a good search.
Yeah, it's a bad name.
Yeah.
Golem's Rulers was probably the best name.
Golem
Sorry.
rulers, sit-on sets, I think Sidon says there's another thing
There's an-
in
exactly,
harmonic
in Fourier-
analysis called
in
Sidon
Fourier
Fourier
set.
is the-
analysis, so there's an
Yeah.
overlap, but nobody else used the world Golem's ruler for anything else.
Yeah, that's a good name.
Unique name.
Yeah, well,
Right, so you-
Babcock sets, that's also there. And there are Edwards sets, which turn out to be B2 sequences without consecutive elements.
All right.
So this-
So you've got that small improvement specifically for Sidon sets, right? The very small improvement in the error. That's a new result.
Yes, yeah, so,
And you think that that's going to be improved on within a month or two.
I don't know of anything coming down the pike, but there's a lot of opportunity. So, what you end up with, right? So the fundamental question that's going on is, so you've got your Sidon set of integers, and you're sliding a window across it, right? And that window has some width, and you are recording how many elements of the Sidon set you can see through the window. And as this window slides, that number, sometimes it goes up by one, sometimes it goes down by one. And the real question is the variance of that sequence of numbers. That is, I think, 95% of the error term.
You gave a very detailed talk a couple of months ago with,
Yes.
very exact pictures of what's happening and what you think the reality is and so on.
Yeah, I'm glad you remember. I'm kind of vague. I've lost track of what I actually said out loud and what I actually just said to myself while I was walking my dog.
So is that very?
It's interesting. This most recent version of Daniel Carter and Zach Hunter, and I'm in there as well. They're working with different window sizes. That if one window size leads to a small variance, then there's another window size that has to have really big variance. And so they're playing that off against each other, which is we are playing that off against each other, which is a really an idea that has a lot of potential, I think. But we're still just playing around the edges. We're not picking up variance around the middle of that sequence.
Is that
Other
variance?
questions? Comments?
Yeah. Is that variance sort of in a probabilistic sense, like you were saying towards the end of your talk, or is this like a different sort of sense of variance?
You subtract the mean and square it and add that up. The only thing you've got to be careful, right? So this window could go from minus infinity to infinity. So you only start where it lifts up from being from 0 to 1, and then you stop as soon as it goes back to being 0. Right, so that gives you it's more than n terms in this sequence. It's n plus the window size, and then it's literally the variance of that. So this is the correction term in a Cauchy-Schwarz inequality. Is how it comes into play.
Good. Lots of interesting questions about sit-on sets.
Yeah, they're not
Next
all
week.
answered yet.
Yeah. Next week, I suspect not many of you know what a coursification of the integers is. So next week you'll
correct.
learn. There are a couple of guys in Germany who have worked on this, and one of them is going to be giving a talk. So it's kind of interesting, actually.
It's not just a usual number theory talk with lots of obscenity.
It is not. No, it's more related to geometrical questions where you look at maps which aren't exactly, or like in metric spaces where you look at maps which aren't exactly isometries, they're sort of quasi-isometries. So they're close to being an isometry, but with a little wiggle room, a little error. And this is a kind of arithmetical analog. So,
Kevin, I
unlike
appreciate your pun.
unlike sit-on sets where you can easily put together a bibliography of 500 plus papers, coursification is a subject where you would have difficulty putting together a bibliography with a double-digit number of papers, right? So, so depending on your point of view, that makes it either more interesting or less interesting. I mean, for me, it makes it more interesting because it's kind of a new idea. But you know, who knows? By the way, when you mentioned me and Chawla's name coming last, Chawla, with whom I have, I think, just one joint paper, but Chawla was the world's most self-effacing human being. And he would always try to put himself last. That was just the nature of his character. And in Selberg's long career, he only wrote one paper with someone else. There's only one joint paper, and that's with Chawla. And Chawla also made that Selberg and Chawla. He didn't think his name should come before Selberg because Selberg was so great and Chawla was so humble. And it might have been a relic of growing up under the British Empire in India, but he wasn't he really, I mean, Carlos might have known him because he was at the Institute in Princeton forever. He was the world's really most self-effacing guy. I mean, he was very sweet, but yeah.
When did he die?
Collected papers are a lot of fun to look at. I mean, there's a huge, they just came out, I think, a few years ago.
Yeah,
They're
someone
great fun to
recently
browse.
put out his
So many
collected
conjectures.
papers. But I've never seen it. I mean, I know at one point I got an email from the editors because as a co-author of one of the papers, they needed my permission, which of course they got. But I don't think I ever saw the bound volumes.
I have them. I mean, you can get them from the Canadian Math Society, I think.
Yeah. No, I know they exist. I literally have never seen it.
There's a nice little book that he wrote on the Riemann
Oh, yeah, I
hypothesis.
remember that.
Oh,
First,
yes.
It has, I mean, this was his own hand.
Yes. One
Right
of the
on
world's, it's extremely interesting, but one of the worst written books in mathematics I've ever seen. I mean, it's just, I mean,
So Mel, you're still recording.
yes,
I don't know if you want to put this onto YouTube,
I will. Let me just actually stop it.
trash talking people's